Okay, perfect. So week 2 of this experiment looking at transformers. So we'll be running through transformers again. I just wanted to start with a little recap of what we talked about during week 1. So we kind of talked a little bit about transformers, why we care about them, what they are. We didn't talk too much about the architectures, but we did talk about the HuggingFace library and the various core pieces in it that we can use. We talked a little bit about tokenizers. We'll learn about those more today. We learned a little bit about data sets. We'll learn more about those today as well. We'll use the trainer again. And then today, we'll be looking more at the actual data and pre-training. So last week I mentioned pre-training a few times, but I didn't really say in detail what it is. So this week we'll be looking at what data you need and what pre-training is. We won't go in hyper depth on the pre-training. That will be next week, but we'll at least talk about the data, what you need, what the goal of pre-training is, and all of that stuff. So that's just kind of level set what we'll be talking about this week. So I have this notebook. I can share this again, actually, for anyone who might have not been around when I shared that the first time. So there's a notebook again. I highly recommend opening it up, trying to run things. Is better if you run it yourself and see the outputs and all of that stuff. So one bit of advice is if you are opening it for the first time, you want to go to runtime, change runtime type, and then change it to GPU. And that will make the final step in this go much faster. If you don't do that, it's not going to complete before your system times out. So with you guys started on that, we'll start looking at what actually is pre-training. So pre-training, as the name suggests, is anything that you do before you actually train the model to do the thing that you want to do. So that can take a lot of different forms. That can be training on a different task. That can be training on different data. That can be doing some initialization step. There's a bunch of different things that you can do that would be considered pre-training, but the way that people typically think of it, in the language context at least, is some sort of task where you're learning about language. And so that can be guessing the next word in a sequence, that can be filling in the blank. There's a bunch of different flavors of that. And we'll talk about that more in later weeks, the various different options, what people have experimented with, what's been successful, and what seems to be the future of that stuff. So pre-training just can be many different things. In language, it might be guessing the next word. In images, we have this ImageNet data set. And that's millions of images and thousands of classes. And so it's this massive data set that's been labeled. You can train against that, and then you can transfer it to something else. And so pre-training can be supervised. It can be semi-supervised. It can be a bunch of different flavors. Pre-training is just kind of the general word for let's do something before we actually train on the data that we have available. So training on ImageNet is considered pre-training. So you train your model on ImageNet, or you borrow a backbone that's been trained on ImageNet, and then you transfer that to some other image task. That's kind of what I want you to think about is just some step before training. And you can do that in images and text and time series and whatever else. If you find some creative way of learning something from your data without needing to label it, you can generally do better on the data that you do have labeled. So there's new interesting stuff on contrastive learning. So you might do something where you take some input, you slightly perturb it in some way, and you teach your model to map both of them to the same space. So if you have a dog, you rotate it 5 degrees to the left, it's still a dog. So you teach your model, let's make the outputs of both of those be similar. And so not too much detail on pre-training. We'll talk more about the details of language model pre-training in later weeks, but I just wanted to say this is a whole slew of things. It can be many, many different options. And so one of the important things that I want to mention is like your whole goal is to capture some knowledge that can then be transferred to a new task. So you start with a model, and most people have learned about like randomly initializing weights of a neural network. That's a decent starting point, but you probably want something that's more informed than that. And that's kind of what pre-training does for you, where it's like, do you think that a random starting point is better than a model that has learned about languages and images and other things already? Probably not. Probably you want something that has already learned something about your domain a bit, and that will transfer to other things. And so it's kind of interesting that you can get this transfer on things that you wouldn't even expect. Like ImageNet has images of cats and dogs and birds and cars and all kinds of other stuff, but it has no images of cells or various different cancers and stuff like that. But you'll find that even a model that has been pre-trained on ImageNet will be better at these other downstream tasks because it's just generally learned something about images, where it's like now it has something that can handle edges or corners or textures or colors or something else like that. So it's better if you can get pre-training that is in a similar domain to what you actually want to be doing, but it's been shown that even just learning on anything is actually very good. And so there's actually, I don't have the paper linked, I'll have to add that, but there's been some work shown that you can even do synthetic pre-training. So you can take something and you can just kind of generate images that train in an interesting way and teach your model some patterns. And just doing that will be better than random initialization, because random initialization just doesn't capture anything interesting in your model. And so just kind of giving your model some patterns to learn will put it in a better spot than complete random noise. And so people have figured out really interesting things to do with pre-training. It's kind of a big problem that a lot of people have, is that you don't have that much label data. And so people have found interesting ways to say, I have this big pool of unlabeled data. I don't have any labeled data. Let's try to train something that can learn from this unlabeled data in a useful way. So if any of you have heard of the paper Whisper from OpenAI, they actually have built a really, really good speech-to-text model with just a bunch of unlabeled data. They actually, everyone else is using this small set of label data, and they said, let's actually find all of this unlabeled data and try and scale that up. And it turns out that just with unlabeled data and the right creative way of formatting it, you can make a model that's just as good as a bunch of supervised models. And so that's something that I think is important for people to start thinking about. Is a lot of people are worried about label data, but there's actually very interesting things you can do with just generic scale of data. How do you build something useful out of stuff that you don't have any labels or annotations for? So Whisper is a really cool example. If anyone wants to look at that paper, there's the link. And there is, so I just wanted to show like, what is the actual impact of pre-training? So this is in the context of language modeling again. So this is pulled from the GPT paper. People have probably heard of that. It's another OpenAI model. And basically what this little table from the paper is showing is, here's how the model performs when we do the language model pre-training, and here's how the model performs without any pre-training. So just randomly initialize, what I was talking about earlier. And you can see that the difference in performance is very large, especially on this COLA task. And on some of these, it's like dramatic. It's like this was a complete failure before, and now it's doing quite well, actually. And so this is basically showing that this language modeling, this pre-training step is very important. This is like core to the whole architecture. It's getting you started with a whole bunch of knowledge. And this is very, very important as your label data becomes smaller. So you might have a data set that's only 1,000 samples. And so you can train a little bit, but it's not extremely, there's not much for it to learn from if it only has 1,000 samples. It's not going to learn all of language in those 1,000 samples. So if you can take something that understands words and their similarities and the context and all of that stuff, it's going to be much, much more powerful than something that you are starting from scratch and only has 1,000 samples to learn from. So there's a question about the column headers. So all of these are different tasks. So basically they've taken this pre-trained model and then they've said, let's fine tune it on a bunch of different tasks. So this COLA task, SST2, MRPC, STSB. And so they have this other data set. It might have 1,000 samples, it might have 50,000, and they train it on that label data set and they see how it transfers its knowledge to that. And we could find those data sets on the HuggingFace dataset hub if we want to, and we could look more specifically at what exactly those tasks are doing. But I think that the story is good enough on its own that you can just see that this performance has gone significantly up for many of these tasks. It's just a much more powerful model when you do that pre-training.
I have a question.
Yeah.
So so we have a average score and then method, and then underneath the method is that what are the, it's like F1 score for MRPC, for instance, and accuracy under SST2. So they're different metrics for each column.
Yeah. So each of these are completely different tasks. So this one, I'm blanking on what some of these are. I haven't interacted with these data sets specifically, but each of these are different tasks. So they probably have different associated metrics that they care about.
Cool, makes sense.
Yeah, and I'll just add, so each of these is a benchmark. So multiple people can test their models against it. They will have a training set and a test set. So you can train, fine tune on that training set, and then it should be apples to apples when you report your results using the metric they tell you to use on the test set that they tell you to use. And as long as you don't cheat, then basically, everyone's got a fair set. So these are all benchmarks.
Yeah. Yep. Thanks, Ted. So we touched on pre-training, how powerful it is. Now the question is, what exactly do you do to do pre-training? Well, I would say that the first step is you have to gather some data. And so what are the characteristics of the data that you're looking for? For our language specifically, one of the biggest things is just the scale. You want a lot of words so it can learn a lot of vocabulary, a lot of different examples of those words. And the other thing is you want it to be high quality. So you want it to not just be gibberish. You don't want a whole bunch of kids' books or only small snippets from Twitter. You want variety and you want quality. You don't want stuff that is probably like, you might find a bunch of filler text on websites and stuff like that. You want it to be actual writing in this context. And so what a lot of the research groups have found is successful is this books corpus data set. And what this basically is it's a whole bunch of unpublished books that have kind of just been collected together, and then you can train your model against these. And because it's varying writing of different genres, and it's presumably reasonably high quality, it's not random internet nonsense. It can learn the proper grammar and structure and a whole bunch of vocabulary. And so if you look at all of these different models, various famous ones, so GPT used book corpus, BERT. So these are all excerpts actually directly from the paper. So BERT also used books corpus. Roberta also used the book corpus. And then if you look at these, they actually added on additional bits. So BERT added on English Wikipedia. And just to understand the scale of these, books corpus is 800 million words. All of Wikipedia is roughly 2,500 million words. And then if we look at Roberta, it actually takes both of these. It takes book corpus, English Wikipedia, and then it also adds in CC News and a few other data sets. And if you look at everything that they add up, this is like 160 gigabytes. Yeah, it's 160 gigabytes of text at that point. They've gathered in just tons and tons and tons of text, and they pulled some of that from that book corpus, some of it from Common Crawl. So Common Crawl is this data set where they basically just scrape the entire internet. They go through and they just point to every link that they can find, and then they download the web pages or the documents or the whatever's there. So Common Crawl is this massive data set of the entire internet. It's terabytes of data, and they can go through and they can filter out to just the website text, just the news text, just the document text, just they can filter it in many different ways. Just looking at this evolution, we can see that GPT was the first one, and it started just with the books corpus. BERT added in the English Wikipedia. Roberta added in all of this web text that scaled it up a whole bunch. So we can see what that looks like. And if anyone wants to go and actually interact with the book corpus, this is one of those things that's on HuggingFace. The data set is just available. So if you want to download this and interact with it, it's trivial. You go here, you import data sets, and then you load the data set, and it will just download the whole thing for you. It has a train, test, and validation split already set up. All of that is prepared. You don't have to do anything fancy with that. So it's actually pretty nice. My warning on this though is it is like 6 gigabytes. And so I originally started our demo to download that and process it. But the first time that I did that, it downloaded fairly quickly, but then it has to prepare all of the splits, and that was going to take 30 minutes. So I ended up pointing us at different data sets. So one of the things I want to point out is if you go to this, the dataset hub, you can look at all the various different tasks. The one that we're interested in is this fill mask. And so you can see that there's all of these different data sets here. One of them is the book corpus one. If we look at wiki text, here's another data set that has a whole bunch of text from Wikipedia. We can look at C4. C4 is kind of an interesting one. So this is something that came from Common Crawl. So what I was talking about before, that big scrape of the entire web, they took that and they filtered it down to just the text, and they did some other things to clean it up. But if you look at this, it is massive. It's 305 gigabytes just for the English. And depending on which file you're downloading, it can just be a colossal file. So if you do ever want to interact with this, there's some instructions of how to do this streaming rather than downloading the whole thing at once, which is kind of nice. so this is a good place to start if you want data sets to pre-train against. So for the demo we'll be doing today, I actually went to the this Amazon US reviews one. The multi, yeah, I did the multi one. And so this one isn't too huge. It's actually quite a bit smaller. So it has 200,000 reviews from each language, and it's got several different languages in it. So it's got English, Japanese, German, French, Chinese, Spanish. And so I figured that would be kind of an interesting branching off point for anyone who wants to try something new, is we kind of have this multilingual base that we can start off of. And so from that, I'll start getting us into the actual code. So first step is we'll just install the data sets. And then from there, we will do that step that we saw on the HuggingFace panel before, where we import the data set library, and then we load in our data set. And so this load data set step, we're just saying, okay, load this data set and with this parameter. So by default, it's starting with English, but you can swap this out for Japanese or Chinese or whatever the other options were here, French, Spanish. So if you want to experiment, you can change that right here, and then you'll get a completely different output for the rest of the notebook. The scale of the data will be similar. You'll get similar results, but with a different vocabulary, different set of reviews. So if you want to play with that, that's a reasonable kind of breaking point to try something else. So here's what the data set looks like. The data set is this HuggingFace object that has training set, validation set, test set already broken out. So we have 200,000 training, 5,000 validation, 5,000 test. And then we can see all of the different features of this data set. So you could actually do various different things with this. You could try to predict the number of stars. You can do stuff with all of these different fields, but the one that we're most interested in is just the review body. So that's the actual text that was inside of that review. And so I loaded this in, and then I just kind of did some simple checks of what's inside of this. So if we look at this, we have, I believe it's like 35 million characters. But then if you just split on spaces, you see that it's about 7 million words. So if we compare that to the book's corpus that has 800 million, we're like 100x smaller than the book's corpus because we only have some reviews. We don't have thousands of books. And then if we look at the English Wikipedia, we're kind of another order of magnitude smaller than that. And then the C4 data set that I mentioned before, this Amazon data set, I don't remember exactly what the download size is, but it's like probably under 500 megabytes. And the C4 data set can be a terabyte plus. So just to understand, we're playing with a grain of sand, and there's a whole sandbox out there. And so I just wanted to point out there's the C4 data set came out of the T5 paper. And this T5 paper, if anyone has the time, I think is actually a very good place to start if you want to dig into some of the details. So I don't want to scare people away, but it is 67 pages, but I would say that if you want to just learn from the ground up, it kind of explains everything, all the history of things that people have tried. They recreate a bunch of efforts. So if anyone has a lot of reading time, this is one of the papers that I would highly recommend reading, because they do a whole bunch of ablations, and they basically say, what if we do this? What if we do that? What if we scale this up bigger? What if we change the pre-training task? What if we do whatever? And so you can kind of see the parameters and which ones actually matter, and what has a big impact on training and what doesn't. This one for me was kind of an eye-opening paper, because people have done all this work trying to change the architecture and do all of these other optimizations. And then I kind of looked at it and it was like, well, these things don't really matter at this scale, where it's like, do I choose 10%? Do I choose 15%? Do I choose 25%? And then they're all within like 1% performance. And it's like, okay, some of these details are not super important. You can get by on certain things. And so this is another one that I think is kind of interesting. So like we're talking about this huge C4 data set. And so they're showing 745 gigabytes. And then you look at its performance, and it's good. I mean, I would say that it's usually the best. But if you look at, you could get the same thing with 17 gigabytes. So it's actually interesting to see that this whole 6.1 terabytes, if it's unfiltered, if it's not a high quality data set, you will do worse than a 16 or a 17 gigabyte data set that's been filtered and curated and is high quality. So I think this paper is worth looking through. There's lots of different conclusions that you can come to just by looking at the different charts that they have. So I wanted to give a shout out to this one. It's very, very long, but there are interesting conclusions in there that I think are highly generalizable. So there's the T5 paper. That one's pretty interesting. And then from here, we'll start looking at the tokenization step. So we've talked about this a little bit. It's the process of taking the words and splitting it up into their sort of core chunks. And now we'll actually be training one of these to build a vocabulary. So in the past, I talked about Bert had that 30,522 vocab size. That didn't come just out of thin air. They did some training procedure to figure out which word pieces are useful, which give us good information. And so we can look at how you actually set that up. So we'll start with this from the tokenizers. We'll import the byte level byte pair encoding tokenizer. So there's different options here. There's the word piece tokenizer and the byte pair encoding tokenizer. You can see the differences in this discussion post here, but it's not really material. I kind of just wanted to get us started on one of them. So we have this tokenizer, and then I hard-coded a vocabulary size. So this is actually a very small one, just 2,000. But I just wanted to get us started. And so basically what this is going to do is it's going to start building up a vocabulary by looking at the frequency of things and building that vocabulary up so it can capture as much information as possible. And so byte pair encoding and word piece do this a little bit differently, but just understand that basically what this is doing is the tokenizer has a vocab size and is trying to figure out the word pieces that cover the most area and the most common character pairs and triplets and larger. And so we can run this very easily by just taking our text. So I just pass in our training text to this tokenizer train from iterator. So this is just a list with all of the text. And then I tell it the vocabulary size, and then it will actually build that vocabulary for us. And then we can save that out to a tokenizer file. And if you guys ever go to the HuggingFace model hub, under the directory for every different model, there will likely be an associated tokenizer and its vocabulary and its config. And so you can see when we saved our model, we got a certain vocabulary output, we got this merges output. So if you look in the if you look in the model section over here, we can look like BERT base uncased. We look in the files. We can see that they've got their config JSON and their tokenizer.json and their vocab txt. And so we can look at this. We have a smaller one. Yeah. So it will output various different files that kind of define exactly how you expect the tokenizer to work. And this is valuable to save because you want to make sure that you keep your vocabulary the same when you actually deploy the model. You don't want a mismatch because that can completely break the understanding of your model. So very, very important step to keep a copy of this, or else your model will end up completely messed up. So here's the vocabulary of the model that we just trained. And so you might see this weird G with a symbol over it. This is because we're doing the byte pair encoding, which is looking at it at a byte level, and it ends up with this weird output. If you did the word piece one, it wouldn't do this. So just putting that out there. It's going to look funny, but ultimately that's just an artifact of the word piece stuff, and it will go away once we do the decoding. So we can do the step
Ryan?
that we, yeah.
Quick comment. I think some of these tokenizers, they have a special character that indicates not only is it LOVE, but it's at the beginning of a word or at the end of a word.
Mm-hmm.
So if you see underscores or these funny things like those G's, oftentimes that's what it means. It either, or sometimes I see like pound or double pound. That's indicating that either it was at the beginning of the word, or sometimes the opposite. Like if you see, like, what did you say last week, like ology or something like that. So if you see like poundology, that means that it's not a word by itself. There were other letters, and this is just a suffix that appears in part of inside of a bigger word.
I don't know if I have it up anymore. But yeah, there's actually a way that you can define the prefix and the suffix on these, but this is actually not the same thing. I toyed with that. And this is unrelated. This is just kind of an artifact of using the byte pair encoding. I was looking at I think I might still have that up. Yeah, I do. So I was looking through this, and people are complaining, why does my thing look weird? And they're just basically saying, yeah, this is expected. This is just how byte pair encoding works. So if you get that spit out, that's just how it works. So I'd have to look into the details specifically why that happens, but in this step, you can actually define a prefix and suffix. And the one that I trained, I actually don't even have that. So you might see a scenario where you do see a pound in the front or a pound in the back to denote a continuation of a word or a word that's going to be continued. So yeah, good point, Ted. We can look at things like we did last time, where we say, okay, let's encode our text that we have here. Last time we looked at it, and so we can see here's all the IDs. So these are the indexes of the words, and then we can also look at the tokens. So how it specifically broke up the words. And then we can go backwards from these IDs to the decoded output. So when we decode the output, it looks normal again. There's a question for the link again. I'll drop that in the chat. Okay, Ted's got it. Never mind. There's another question about the unused in the vocab.txt. I don't know why that is. I have seen that before. That was in the BERT one. We don't have that in the one that I'm doing right here, but in the BERT base on case one, I did see that there was a bunch of those unused. I'm not sure if it's characters that have been masked off for some reason, or I don't know exactly what the reasoning is behind that. But
for some of those unused tokens in the transformer ones, there's supposed to be a way that you can program your own vocab words. Like if you have custom vocab, you can kind of train your tokenizer. And there's supposed to be some like unused words in the dictionary there. So essentially the point of them is that you can retrain them to have their own embedding. If you have like out of domain issues, something like that, you can kind of train your own vocab words in there. It's a little bit more complicated to do so, but I'm pretty sure that's what those are for.
yeah, so it's if you want to add stuff after the fact.
Yeah, like
potentially.
let's say that like you have a word that's used differently than normal in your use case. Like let's say we have a code name for like a team and we call them like Bravo. Bravo might mean something very different in our use case than what it does for what the model had understood. So there's different techniques where you can either, you know, retrain the embedding itself, or you can map that word to one of the unused tokens, and then you can train it based on your context. Or if you just have stuff that isn't picked up properly with the tokenizer itself, like let's say you have like just a random assortment of characters that pop up, like whether they're like internal data codes, like 62.A5, something like that. If you want that to have significance, you can use those unknown tokens and train them to have some sort of representation of how they should be interpreted. That's kind of what those unknowns are for.
Yeah.
Mhm.
Cool. So yeah, here's the decoded output again. So this looks normal again. We've done the encode, we do the decode, we can see that the text looks normal. We install the transformers package, and then we can go in and we can actually reload the tokenizer that we just trained from files. So we say load our vocab, load our merges, and then process it so that it can be in the correct BERT format. We'll set the max length to 512, and then we will actually get to the point where we're defining what our model looks like. So this is the part where I I was wrapping this up like 30 minutes before time. So not all of this is polished off. A lot of this has been kind of directly taken from the documentation. So this is basically defining what our model is going to look like. We have our vocabulary size, and I was getting out of index errors, and I was seeing that I was consistently getting token 2001, even though our what's it called? Our vocabulary size is only supposed to be 2000. So for now, I just added on +5 just to make it so that our model will represent everything. But I'm going to have to look through there and understand exactly why we ended up with tokens that were going out of the range of vocab that we were supposed to. So I'm starting with a Roberta model. I mentioned this one earlier. And here's the parameters. We talked about most of these before. So the number of hidden layers, that was the L that I talked about a while ago. Normally you might do something like 12. That's kind of a good starting place that a lot of people use, but I'm doing everything small just while we try things out. So we load in the tokenizer, max length of 512. We'll set it to truncate because we want it to be a maximum of 512. So if it goes over that, it will cut off the right side and we'll only have 512 tokens. And then this is the part where we actually load in the model. And so we'll be doing Roberta for masked language modeling. And so basically what this is doing is it's taking that Roberta base model and then it's adding on a layer at the end to do that actual language modeling. If we look at the parameters, we can see that we've got 45 million. So in the grand scheme of things, it's pretty small in comparison to BERT, that's 110, or BERT large, that's 300 something. So we're operating on a fairly small space just so we can train the model. Then we have to tokenize using that tokenizer that we did before. So what this will do is it will take our data set and it will turn the whole thing into those IDs that we saw, and it will truncate when it needs to. So this will make it so the data lines up well. This is a function that I borrowed from their documentation that will basically group up the text, so it's good for the masked language modeling. I have to spend some time reviewing exactly what this does. We'll look at the pre-training more in later weeks. I kind of wanted to just speed through so we could get to the actual pre-training, and then next week we will talk in more detail about exactly what the masked language modeling is, causal modeling, and we can do that training and look at exactly how we set things up to train it more efficiently. But for now, I just wanted to show here's the preparation of the data, here's how we get it into the model and start something pre-training. So this is our data set that we've tokenized now, and we have all of these extra columns that we don't want. So I'm just removing them. And then we apply this group text function to everything. And now we have our data sets that are actually ready for language modeling. So this map is kind of a neat little trick that will apply it to all of the different data sets. So we have training, we have validation, and we have testing, all of those available. And so map will actually run this against all three of those. And on top of that, it's actually running 4 processes in parallel. So it will cut it into 4s and then run them all at once. So this map function is actually very useful for speeding things up. And it also does well in that it will apply the same exact thing to all of your different data sets. You don't have to write a whole bunch of code to apply it to each of them individually. And then we start getting into the point where we're doing the actual training. So last week we looked at the trainer. This is kind of a substitute PyTorch training loop. So you can just use the trainer instead of writing all of your own training logic. You don't have to do the whole forward and backwards pass and all of that stuff. And then the training arguments was that thing we looked at the other day where it's got a whole bunch of options with defaults in terms of the learning rate and weight decay and how you want to evaluate and a bunch of that stuff. And if you want to overwrite any of them, you can just enter in the various different options. So we'll name our experiment Amazon reviews. We'll evaluate every epoch. Our learning rate is this, our weight decay is this. And then there's this nice function from transformers that will actually do all of the masked language modeling stuff for us. So just to preview what we'll actually be doing in this training setup is filling in the blanks. So GPT has this task causal language modeling where you're basically saying, okay, given these 4 tokens, what's the next one? So that's causal language modeling, just a preview. We'll talk about this more next week. But the masked language modeling is a different one where basically you're saying, here's all of the tokens. Some of them are blanked out, some of them are swapped out. And the goal of the model is to actually fill in the blanks. So some of the words are essentially hidden, and then it says, given these context words, what was in between there? And so this data collator for language modeling, it will actually do that for you, where basically in the data loading process, it will give you a copy where some of the words are masked out, and it also gives you the output of the original text. So your model will be given that masked input, full output, and you're trying to guess what that full output was. So this data collator is actually packing a whole bunch of logic inside of it. And so now we can kind of put all of these pieces inside of the trainer and then simply hit train, and we'll see how the performance does. So the trainer, we input the model, so that's that Roberta model that we defined. Our arguments, that was right up here. These are the parameters that we set, and then we give it a training set, a validation set, the ones that we already defined, and then the data collator, which will actually do the job of kind of loading these data sets in and formatting them in the right way. And then from there, we hit train. So we just do trainer.train, and this will go through the process of trying to train against this data set. And so this is actually the first time I'm getting to see these results because I set this to run 30 minutes before, and this took like an hour to run. So this is the first I've seen epoch 2 and 3. So basically what this has done is it's used our vocabulary, our model, and tried to learn this fill in the blank task against this data set that we have. And so you can see that our training loss went down, and our across the next two epochs, we didn't go down very much. And my hypothesis of why that happened is we only did a vocabulary of 2000. So the model doesn't have very much expressiveness. So if we scaled up our vocabulary 2x and we scaled up our model even larger, we would probably get better metrics on this. So this is kind of the skeleton of how you would get started on pre-training against your own data. So yeah, this is fairly small start, small vocabulary, small data, small model, not very many parameters, not very much training, or only 3 epochs. But this only took about an hour, and you can see that it's starting to make some progress. I probably have to look at this and understand why it didn't go down more, though. I would have expected it to go down more. So yeah, this is what I have for today. Any questions? Anything anyone wants to go back to?
I'll jump in with a quick note, and people can think about questions. Just to remind, in this case, Ryan, I'm not sure if our model is still too big and we don't have enough data, and maybe that's why it might take many more than 3 epochs to start converging. But I did want to also note that this is a mass language task. So I've deleted a word. Can you guess what word I hid from you? And I haven't seen stuff written up on the models that were trained this way, like BERT, as to actually how good they got at this task. It's entirely possible that even though they learned a lot about language, that they still did fairly poorly at this task, because for any one given word, there might be a lot of synonyms. There might be a lot of possibilities for what word you could put in there. And so the training loss might not be indicative of how well it's understanding language. I don't know if periodically you need to like checkpoint and then test it on something else in order to see. if it's actually learning. Does that make sense?
Yeah. So this is actually directly from the BERT paper. So the metric that we're using is perplexity, and we'd have to go and review exactly what that is. But you have to know that lower is better, and so this is directly from the BERT paper, the perplexity that they're getting. So they see 5.84, which is not super far off from what we're seeing here. So it looks like it's reasonable, actually, given that this is their smallest model, and they see better performance when they add more layers and larger everything. So it looks reasonable, the number that we got. But yeah, maybe more training, maybe bigger vocabulary, maybe bigger model. But yeah, so you can actually find these numbers in most of the papers, but most people don't care too much about them because it really depends on what data set you're applying against and stuff like that. So it's not apples to apples. You can't say that Amazon reviews look similar to book corpus, for example. I linked this one in the notebook as well. But this is this whole paper is just on the scaling laws. So we've started very small, and then it kind of shows you how does performance increase with data set size, more tokens, more parameters, more compute. So that's kind of the stuff that we're looking at here. Is we started very small. What happens if we scale across the data axis? What happens if we scale across the model size axis? What happens if we train it for 100 epochs instead of 3, for example? And they have some interesting conclusions in this paper in terms of what's optimal, what trade-off do you actually want to make in terms of, do I want to train a smaller model for longer, or do I want to train a bigger model for shorter? Do I want to train against more data, or do I not care that much? So they have some interesting graphics here, and they've shown that model size is like very, very important, more important than just about anything else in terms of predicting your performance. So you tend to actually want bigger model and less training than vice versa. So this paper is linked in the notebook, but just figured I would talk about this a little bit. And they have some pretty convincing graphs too, showing that in the past people have used RNNs and LSTMs and GRUs, and they have pretty convincing statements that transformers are just better at these kinds of tasks. So I've never been super convinced that we couldn't just do a lot of this stuff with LSTMs, but these graphs are pretty convincing that you just get better performance out of transformers in a lot of different contexts. So yeah, wanted to call out this paper as well.
Sorry, Ryan, what paper was this again? I think I cut out for a second.
This is scaling laws for neural language models. I believe I put a link in here somewhere, and if I didn't, I'll add it later.
Cool.
I thought I put it in here, maybe not. Yeah, I'll add that.
Cool. Yeah, for anyone that's interested in training like these general use large language models, typically when we fine tune them on any other tasks like classification or whatever, you're going to be using other loss metrics like cross entropy loss, which are easier to interpret. The thing with perplexity is that perplexity is used when you have something like you're just training this model in general. What it's essentially predicting is like, I guess a way to interpret it would be like the model's confidence in its outputs based on what word it should predict out of its vocab. So it's not like really a great useful metric in terms of like being translated into like a metric of like production where you could look at like, okay, the accuracy is getting better, but it more notifies you of issues that you might have. Like if your perplexity starts to go up, your model is starting to become like quite uncertain, and then it'll spike up pretty quick and it'll start like printing out gibberish. So it's more of a metric that you just want to keep a sanity check with and make sure that it's steadily decreasing, or it's kind of staying as is and it's just picking up on more learning. But typically it's not used as often. I used it a fair bit when I was like retraining these models from scratch, but it's a little more complicated to understand. I think the HuggingFace course that goes over transformers that came out last year, they have like a quick video on it that's only a few minutes long, but they share quite a few links to anyone that might be interested in reading up more on it. I was like researching it a little bit a few months ago, so I have some info there, but essentially like it's just kind of the model's confidence in its predictions. That's kind of how you can interpret perplexity.
Thanks, Boo Boo. And without like making a joke about it, I have found perplexity to be a pretty confusing thing to try to understand. I think I've seen stuff that says that I mean, depending on like your vocabulary size or something like that, but that I think generally thinking somewhere around like what 8 or something like that is kind of like a bad perplexity, like sort of you know, random guess level kind of a thing or something like that. So if you see perplexity scores, just so you have a sense that like I think 2, 3 is state of the art and 8 is like random guessing. So it's not a number with a very wide range. Like an improvement of 1 in perplexity is a pretty huge thing, and it's an exponential kind of a thing. So you can think of it like the whatever, like earthquakes, like the Richter scale, right? Like it's a pretty big deal to make a jump of 1 in perplexity.
It's kind of interesting, actually. Perplexity doesn't typically scale across all models the same, if I'm not mistaken. Like the perplexity of a model that's like, let's say like 125 million parameter GPT model versus like the 1.3 billion parameter GPT large. If you're fine tuning both on the same task, the perplexities will both be somewhat like similar. They'll be very close to each other, but then one will still outperform the other. Instead, when you're training them and having them like a custom and learn to your specific use case, they're kind of outputting their own perplexity for their own task, as opposed to the other one where it might be on a different task. So it's a rather tricky metric to like compare with as well. It gets more complicated than just straight comparing, but I think your general point of just the lower the perplexity, the better it is. If it gets high, it's just randomly guessing. And yeah, you kind of just monitor it and make sure that it's steadily decreasing. And you know, like decreases of like a whole point are pretty high. But another thing that we have to realize is like when you fine tune these on a like a very large data set that the model wasn't originally trained on, one thing that we'll notice is that perplexity actually starts very high. Like for your first batch or so, first step, you might have perplexity of like 25, then it'll go down to 8, then it'll go down to 6. So it'll quickly come down to like sub 5, but then you just want to monitor that decrease. So it's complicated, but just kind of know that it should be like sub 8 and go down slowly. And comparing between models is kind of difficult if they're not all pre-trained with the same data set.
Thanks, Vivu. I'm just skimming through. I have the various papers up, and I was trying to see if I could find their perplexity to compare against. So this is Roberta, and this is the numbers that they report in their work. So I was just peeking at it to see if what I had was even moving in the right direction.
Yeah, and I don't want to go down the rabbit hole, Ryan, but I think with your small vocabulary size, you've actually kind of goosed your perplexity numbers because you've reduced the base it needs to guess in. And so I think your perplexities might not be as good as think they are because you're doing it in a smaller vocabulary.
Yeah.
It's interesting. I was like, Sorry, go ahead.
What I just did is I just scaled the vocabulary up to 20,000 instead of 2,000, and I made it 12 layers instead of 6 layers. So it's going to take an hour and a half to train now, but we'll see what it gets eventually. We'll see if it's better or worse. And to your point, the 2,000 means that it only has 2,000 vocabulary to guess from. Now it has 20,000, so it's actually a much harder task, but we'll see.
Yeah, I was gonna say I had a discussion with someone that like did his PhD thesis on a task where he had to like go deep into perplexity. So I was like bouncing ideas off him, and he also found that when you shorten the model's vocab output size, you would think that perplexity would go higher because there's only so many words to guess with. But then you also have to deal with the fact that okay, now the model might just not have a proper word that it should fit into the gap. So it's also struggling because it's not too confident on its prediction because it might be the best option it has, but it's still not a great filler word. So there's little things like that as well, but that goes too far down that rabbit hole that we'll probably save for another time.
Yeah.
This is really cool code, Ryan. So I mentioned something in the chat. Do you know if there's a function that easily do the correspondence between your input text and a given token? So like if you were just looking at the 30th token, because it's not one-to-one with words, it's not always that easy to know, like, well, what the heck is the 30th token? Is that the 15th word? Is that the 20th word? Where is it?
I believe that there is a function that will do that for you. I know that the tokenizers output a whole bunch of offsets to show you which is which. I'd have to look at that.
Okay.
Yeah, I'm not sure.
I've done the same thing where I've like had some helper functions that'll print out like, okay, these tokens are offset by this much and this token corresponds to this in my input. So it wasn't necessarily a built-in function. If I remember correctly, I think I probably found it off somewhere on the internet and altered it a little to my use case. But you can definitely write something like that. If I, it took a few minutes to write it up and find something, there might be a built-in function that'll do it all for you in one line. But when I last checked, I had to do it myself. But at that time, HuggingFace also just wasn't as big with a lot of these functions. But
Yeah.
if there's not a function to do it, it's not too difficult to just manually link up with the data that it outputs.
I'm hoping by now it's like a built-in thing, because it is kind of annoying to have to try and figure that out.
I think the other thing is that most people just get to the point where you just, you tokenizer dot decode whatever your input is, and you see, okay, this is this word, matching it to like the index of the input list and stuff. There's not that many people that go to that level, I'd say, but yeah, it's cool. They have a lot of functions on HuggingFace that I'll like write up some custom code to do something, and then 3 months later, I'll find a function that does exactly what I tried to write up myself, and I'll be like, I wish I had seen this earlier.
Yeah. No, I mean, imagine that you're playing with this and that you've trained it some, and you say, gosh, I want to see like like the attention weights for where I have a pronoun. So I have like the word it, and I want to see, which words it's pointing to. Well, like, you can't do that unless you actually know which words the tokens correspond to.
Yeah, that's definitely a thing that, if I remember properly, I was having this discussion with someone else where they were kind of irritated with how Hugging Face has their implementation of transformers and how difficult it can be to pull out attention of specific words at specific layers and stuff through their functions. So a lot of researchers will, handwrite their stuff without Hugging Face to be able to pull that stuff. And we were having that discussion, and I think the end that we came to is kind of HuggingFace also wasn't really built for that purpose. They're more like open end. Here are the tools to do output, not really to like research deeper, which is kind of where we left it. But it's definitely interesting. They have a lot of stuff out there that a lot of people probably won't use, but they have nice library.
Yeah, thanks. That's a fair point. Like they do make it really easy to get started, but maybe if you're a researcher, you want a little more fine-tuned control.
Mhm.
It looks like, I'm not sure if this is exactly what you were asking, Ted, but it looks like this is roughly
Mm,
what you were saying, where it was like, I don't know if I have this example still up.
Yeah, it would
But
convert.
like if
the
you
index
were
of the
saying
token.
what is the token in this position, it looks like it would map it to back to that is the seventh word or something like that in the text.
mhm.
It looks like that's what this function does. There's a whole ton of stuff in transformers that I've never interacted or found a use for, but they cover a massive space of here's everything that people have ever tried.
Yeah.
Some of their more niche stuff is pretty cool too, like their whole accelerate library and stuff. Not a lot of people will use it, but for what's supported, it's really nice. If anyone's ever bored and wants to read Hugging Face blogs and go through their documentation, you can learn quite a bit doing it.
Anyone else? Any questions? Anything?
Thanks for the presentation, by the way, Ryan.
Yeah, of course.
All right. Well, then maybe we'll wrap up the formal part here.
Sure. Thanks, everyone.